Math 126 students, I have this idea to make a few short videos on error bounds, try to clear up any lingering confusions you have. Do please also consult what we've done in class. This is just an introduction. So I'm going to make 3 small videos about error bounds because there's really 3 main types of questions. There's one where we give you the interval and we ask for the error. There's one where we give you the error and we ask for the interval. And then there's one where we ask you to find the first n that makes the error small enough. So I thought I could make a short video on each one. That's basically what my test prep is doing in class this week. So hopefully you're practicing that with your TA. But just to give you a little more reinforcement, those are the only 3 questions that have to do with error bounds. Before I did that, I wanted to make a video where I just gave an introduction. So Taylor Polynomial, this is the Taylor notes from our Math 126 page. We've already talked about this, so apologies for the scrolling here. But in the end, we were trying to estimate this error. And I've shown you lots of visuals in class about this. And we had this so-called tangent line error bound. Now, I know it's a lot to look at. It's a lot to take in. You had to find a bound on the next derivative. We've used it quite a bit. If you missed it, I did outline the proof. The proof is this. It's in these notes as well. The proof is this integration by parts. It's this kind of clever maneuvering. Okay, but the bigger proof is you can keep doing integration by parts and you can keep this process going. And then you can ask what's the biggest the error can be. And that's where we're approximating. We're saying, well, in general, the second derivative doesn't have to be something nice, but if we can find a bound for it, we can replace this with one number. And that will definitely give us something that's bigger. So that was this whole process. If you missed that, we're using this tool because it's really one of the few general tools we can use. And it's good enough for the process we're trying to explain. So as I scroll down, sorry to scroll through this, hopefully look at this. They do it again in the notes. They continue. They do integration by parts again, and that the half appears. I give another explanation of why that number's there. But in the end, if you keep going, the general process is this. And ultimately it's this. So you actually can prove that the function is equal to the Taylor polynomial and that the error is exactly this. The problem is that's not practical for computing. And so what we're doing when we're doing Taylor's inequalities, we're saying what's the biggest this can be and just replacing that with a number and pulling it out. And then the integral of the other thing ends up with an n plus 1 factorial. That's Taylor's inequality. That's what we've been using. That's this. Okay, so there's a lot of theory there, but all you have to know is find a bound on the next derivative and replace that number. And that'll give you one estimate for the biggest the error can be on the interval. So I will make a video where I just talk about that piece, and then I'll talk about what happens if they give you the error and you have to work backwards. And then I'll make another short video where you're trying to find the n. So this is one part. The other part of it is the Taylor series. But I'll be talking about that in class. Maybe I'll make a separate video on that.